The teaching assistant, I think, is going to be available today between 1:30 and 3:30 for objections. So if you want to see where you lost your points, you can just go talk to the TA about this. I also posted the solution, this Java program as a solution for assignment 2 on the website. So if you want to take a look at how I implemented it, you may look at that code. And assignment 3 is, I announced yesterday, it's postponed. The deadline is postponed to May 15. So you are going to have 6 more days to work on assignment 3. And the last assignment is going to be on protein structures. It's not going to be structure prediction or structure alignment. I'm going to have you write a program, a utility program, which which reads a protein data bank file, a PDB file, and finds interacting residues between multiple chains. Okay, so, but this is going to be, we haven't seen how to do it in class, but this is going to be something very easy. All you'll have to do is parse, get the coordinates of amino acids from a PDB file and compute a distance between, we are going to see it today actually when we talk about structural alignment. You are going to compute the distance between amino acids of different chains, and your program is also going to have an input which is going to be the distance threshold. Amino acids that are closer than this distance threshold are going to be taught as interacting. They are going to be touching each other. So you are going to be getting this distance threshold, and you are going to find amino acids that are closer than this distance threshold between 2 protein chains. So it's like you are going to be finding the list of amino acids at the interface of these multiple chains. So that's the main idea about assignment 4. But I'm going to provide more details, of course, when I provide you the document. Okay, still waiting for the Windows to turn on. I mean, we are used to this now. I think there's something wrong with the updates and with the configuration. This fails every time. Yeah, failure configuring Windows updates, reverting changes. So now it's going to let us log in. All right. Okay, so we talked about 2 of the approaches for protein structure prediction, ab initio techniques and homology modeling techniques. And the last approach I'm going to talk about is threading. And in threading, I told you that what we do is, given a protein sequence, we align this on a template structure and see whether this sequence actually favors this structure, whether the amino acids. So what does it mean that it favors this structure? I'm going to talk about in detail in the upcoming slides. And the main assumption, that's the threading works because the structural templates that we know now covers a wide range of the protein universe. I mean, if the structural templates that we are in the threading approach, we are going to align this sequence of amino acids against all the structural templates we know. So the idea is like this. If I have this sequence, I have some idea. I don't know what the shape is going to take, but the shapes that it can take are limited. There's a limited set of shapes that this sequence can take. This based on threading is based on this assumption. And it just tries, we just try. It's actually very much like the Cinderella story, right? I mean, we have this shoe, and we try to find out who is going to be able to wear that shoe. I mean, threading is exactly the same idea, but I mean, this assumption here is that when you're trying this shoe, I mean, the girls that you're trying on is one of the correct girls. I mean, if you do not try it, if you do not know this girl yet, and you cannot find the correct one. I mean, it may not fit on anybody's feet. So here the premise, I mean, our structural template database should be large enough that we are going to try our sequence and the tried structure on all the structures, and the tried structure is going to be the actual shape of the sequence. If, for example, our structural template database does not contain a similar structure to its actual shape, then threading is not going to be successful at all. So structural, and here this sentence summarizes the assumption of the threading is the number of folds in nature is limited. We do not have many different shapes. Not every protein has a completely new conformation, new shape. The shapes of proteins, when we look at the main structures, they have certain similarities. So if we have this database which covers these similar shapes, these fold representatives, if we try our sequence on one of these, on all of these structural templates, we are likely to find a structure which is going to fit well to this sequence. So that's the main idea. So how do we do it? Okay, and this is this assumption, this basic premise is actually validated. I mean, we can validate this basic premise by some statistics. Here in this sentence says that when the protein data bank had 35,000 structures, like maybe 5 years ago. This statistic is taken from 5 years ago, when the protein data bank had 35,000 structures. 90% of the new structures submitted to protein data bank. Okay, so when they solve the structure of a sequence, they submitted to protein data bank, and 90% of those newly found structures have similar structural folds in PDB. Okay, so it's, in other words, only 10% of them have completely new, not previously seen shapes. Many of them have shapes which have some similarities to already existing structures. 90% of them are like that. So in other words, what does this tell us? This tells us that 90% of the time your threading is going to work. Okay? I mean, if imagine you have 100 sequences, 90 of them are going to have structural similar folds in PDB. Only 10% of them are going to maybe have completely new structures. So threading can work for these 90% sequences because they have similar structures in PDB. So this statistic tells us protein threading is actually promises good results for 90% of the time. Here, again, the concept of threading in summary. We thread. Thread means align or place this sequence. We place this sequence onto a template structure in an optimal way. So we need an algorithm. We cannot just, a sequence can be placed on top of a structure in millions of different ways. So we need to have an algorithm for threading to find the best way to align, to place this sequence on top of this structure. Should I, for example, where are the gaps going to be? Similar to sequence alignment, we are going to try to put this sequence onto the structure by having gaps, by matching certain sequences to certain structures. The length of the structure we have here may be different than the length of our sequence. We may omit certain parts of this sequence that we are aligning. So we need to, this optimal way is a difficult thing. Protein threading, unfortunately, is again one of the MP complete problems. So finding the best way to place the sequence onto the structure cannot be established in an efficient manner. We need years of computation to do optimal way, but we have heuristics which can some intuitive ideas that can give us a good solution. Okay, so a good alignment is going to give us an approximate backbone structure of our protein sequence. And the idea is like this. We have this query sequence. It's a sequence of amino acids. No structure is known. What we do is we align this on top of this structure, this structure, this structure. We try every structure in our template data set. And for each alignment, we get the best score. So each of these structures is going to say, this sequence fits me well. Okay, this sequence fits me well or not. Each structure is going to tell us that. And we are going to pick the best structure among this set as our candidate predicted structure. So threading is the process of placing the sequence onto a structure and computing the optimal alignment score between the sequence and the structure and the shape. If we can solve this problem, this is what I already told. I mean, we can do this. Given a sequence, we can try each known fold and find the best fold that fits this sequence. And because there are only a few thousand folds, we can find the correct fold for the given sequence. And threading is shown. There's a paper that shows this. Threading is MP hard, meaning that it's as hard as the problems that are in the class MP. And in the class MP, we currently have problems with no known efficient solutions. It doesn't mean that they are proven to be non-efficient, okay? This is the theory of computation, theory of complexity. Complexity theory deals with these kind of issues. Right now, nobody knows an efficient solution for these problems. But if someday somebody comes and says, okay, I have found an efficient solution to one of these problems, we are going to have an efficient solution to all of these problems in this complexity set. Actually, last year, there was a paper about a researcher from HP claimed that he has found an optimal solution to an MP problem. But later, he withdrew his paper. I mean, there was something wrong in his proof. But I mean, there are lots of researchers around the world trying to find efficient solutions to these difficult problems. But here, the good thing is that they're all same class. They are the same complexity class. If you find an efficient solution to one of them, it means that you have found an efficient solution for all of these problems in the same complexity set. And threading is not MP complete. It's not in that set. Okay, it's not. I mean, it means that if you find the solution to an MP problem, still you may not solve threading fast, but it's proven that it is as hard as those problems. Okay, it's not as easier than an MP problem. So right now we do not know an efficient solution to solve this threading problem, but what we do is we develop heuristics. I mean, we cannot guarantee optimality, but we may have some intuitive ideas that is going to lead us to a better placement of this sequence on top of a structure. So here are the components of threading. We need a template library. Okay, I need to get rid of this. Okay, so we need a template library. We can use structures from a database classification categories. Scoring function. We are going to have single and pairwise energy terms. I'm going to talk about this, and we need to have an alignment algorithm that consider these scoring function to place a sequence on top of a structure. And we may also need our score, our final score. Instead of a raw score, we may need a statistical significance score, which is a confidence assessment similar to the E-value or P-value in sequence alignment. There are different ways, techniques to improve this local threading, multi-structure threading. I'm not going to talk about those. Okay. So the first step is building a template database. And then this slide summarizes how this threading is done. So we have mainly 3 different energy terms when we place a sequence on top of a structure. What does it mean? What does it mean to place a sequence on top of a structure? It means this. Okay, this is the shape, that these are the 3-dimensional coordinates that you are going to give to these amino acids. What you say is, okay, when you place the sequence on top of the structure, you say that this amino acid M is going to be here, T is going to be here, Y. So you need to follow the backbone provided in this structure to provide 3-dimensional coordinates to these amino acids. So this is how you place this sequence on top of this shape. What happens after you place this sequence on top of this shape? Some amino acids that are far away in sequence are going to be close to each other in this structure. Okay, now the question we ask is this. Do these amino acids really want to be close to each other? Okay, so this is how you place them on this structure. So we need to compute some energy terms. And also, for example, there are global energy terms. Like, for example, you place them, the first question I asked, do these amino acids want to be near each other, is a question. We may ask other questions like, okay, you place this amino acid on the surface. Does this amino acid wants to be on the surface? I mean, in addition to pairwise interactions, we can ask global questions. Does this amino acid want to be buried inside the molecule, wants to be outside? So here, these are, this is ES, that energy term is how well a residue fits the structural environment. Does it want to be on the surface, buried inside the core? So this is the energy term ES. And EP is the pairwise interaction between amino acids. How preferable to put 2 amino acids nearby? Because after you place them on the structure, some of them are going to be neighbors in this 3-dimensional space. Do they really want to be neighbors? That's the energy term EP. And there's alignment gap penalty, which is similar to what you do in sequence alignment. We also have gaps, either in structure. For example, some part of structure we do not use, or some part of the sequence we do not use. We have gaps. You also have a gap penalty. So your total score or total energy becomes a combination of these terms. So how come sequence alignment, when it's sequence alignment, it's not an NP-complete problem. An efficient solution to sequence alignment exists, right? ON square, we have a polynomial time algorithm for sequence alignment. Why is it then difficult? We have similar scoring we have a similar scoring function, and we are again trying to do the same thing. How to put gaps, where to put gaps, which amino acid is going to match with structure. We are trying to, why doesn't dynamic programming work in this case? Any suggestions?
Because dynamic programming needs not so much memory for saving the previous step. But in this case, there will be millions and much more than space time needed for saving all the positions, which can cause
No. We are, this problem, okay, that's a very good question. That's a very good point. We are not trying to find the structure here. Our structure is fixed, okay? In threading problem, the threading aligns a fixed shape with a fixed sequence. We do not have millions of different shapes. We have a single shape, okay? A single shape like this here. This shape is fixed. And we have a sequence. Our goal is to align this sequence on top of this fixed shape. So it's like, if this shape may be of 400 residues long, 400 amino acids long, and your sequence may be 300 amino acids long. So you are trying to do a similar one-to-one matching, similar in sequence alignment. So again, you can have a dynamic programming matrix of 300 by 400 if you want. Here, the columns are going to be the sequences, and maybe the rows are going to be the positions, 3D coordinates. It's an alignment of 3D coordinates, so it can be something like this. If we are going to provide a dynamic programming solution, I can represent my structure at the rows like this. For example, a certain XYZ coordinate, another XYZ coordinates. So on the row, you are going to have XYZ coordinates, which is going to give you the position of that amino acid. And these XYZ coordinates are given to you by the structure. The shape provides this coordinates to you. And you have this sequence MTYK at the column. And the question is, which amino acid is going to have which coordinate? So this matching between this and this means that you are going to put this amino acid at this coordinate. You are going to put this amino acid at this coordinate. So here you can fill a dynamic programming matrix like this. So why doesn't this work? That's my question.
Can be later that we try to make this table.
Uh-huh. Exactly, yeah, that's the answer I'm looking for. Here, the energy term EP makes this thing difficult because a matching here, what was dynamic programming doing? Dynamic programming assumed that if you find a solution here, the best solution up to this point is shown at this entry here. Okay, you are going to have this is your partial scores table. And the score here, after you find it, it says that if you align up to this portion of this sequence to up to this portion of the structure, this is your optimal score of aligning this. And in dynamic programming, we do not go back and change this score, right? I mean, if we fill in a table entry in sequence alignment, this is fixed. I mean, if you fill in this table entry, when you are filling this, you do not say, oh, I filled in this incorrectly. You do not go back and change it. So it's fixed. However, what happens here is that your choices here, your positioning choices here, these XYZ coordinates, some of these XYZ coordinates, an XYZ coordinate here may be close to this XYZ in 3D space. Okay, in sequence, they are far away from each other, but if you look at in the Euclidean, in the three-dimensional space, they may be close to each other. In other words, if you decide your decision here to match a certain amino acid with this coordinate here may affect this score as well. Because your later decisions is going to affect the optimal score that you have found here. So you can, in other words, you cannot divide the problem into smaller pieces and solve it. Everything is affecting, all your decisions are affecting all your previous decisions. So that's what makes the problem difficult. So you need to consider all these possible alignments as globally, as a whole, and evaluate it. If you make a certain change in this solution, again, you need to evaluate it globally and see what happens. And since the number of possible alignments was huge, actually, I mean, even in sequence alignment, the number of possible alignments, if you remember, it was exponential. The number of possible alignments you can have between two sequences, based on how many gaps you can put, which ones you can align, it was exponential. But we didn't need to try all these solutions in sequence alignment because we had this, our alignment choices here does not affect the previous ones. They were local. That was what making the problem easier in sequence alignment. However, this EP term is what this makes really difficult. ES term does not make it difficult because your choice of putting a certain amino acid at the surface or core does not affect any other parts of your solution. I mean, it's just only for that amino acid. So if we didn't have this EP, maybe we could have an optimal solution using dynamic programming. And then what we do is we compute an energy value
for this. For our sequence, we align against all the templates and we find the energies and we predict its structure to be the one with the minimum energy. And here are some results of real results of threading programs. Here is the actual structure of a protein, and this is the predicted structure. As you can see, they're really close in shape. I mean, this is the actual, this is the predicted, actual, predicted, actual, predicted. So threading can get really good, accurate predictions for some structures. But it doesn't mean that it is going to work for every structure. There are also not so good examples. Here, this is the actual structure. This is the predicted structure. Predicted structure contains long helices. It's a long protein structure. And in actual one, we do not have long helices. It could find this part correctly, but not the whole protein structure. So, and what is challenging is that how can you know when it's going to produce good structures, when it's going to put bad structures? I mean, if you do not know the actual structure, we can never know this, right? I mean, and this is why we use, the reason we use computational prediction is that we do not know the actual structures. If we knew the actual structure, I wouldn't do threading. I mean, if I know the actual structure. These results are for validation purposes, but I mean, it's going to tell you give you an idea about how threading works. I mean, it's going to say threading works sometimes, but you'll always have this doubt in your mind as a biologist if you're using computational prediction. It's going to give you some structure, but you will never be able to trust it 100% because of examples like this. I mean, it can sometimes produce bad results. So computational predictions can be taken as a certain clue about the structure, but you need to do some biological more validations to actually verify the predicted structure. There are prediction programs based on threading. Prospect, Fugu, and Threader are some tools that run. There are different variations. Threading algorithms, since the threading is not an optimal solution is not known, different heuristics may be used when they're doing this actual threading of a sequence onto structure. So therefore, we have different programs, different threading programs that does this prediction. And there is this, as you can see, structure prediction is a difficult problem. And there's this competition, critical assessment of structure prediction algorithms. It's a competition in which the structure prediction programs compete. Here is a timeline how this competition is organized. There are structural biologists, so these are the actors. There are structural biologists which actually solve the structures experimentally. Okay, so these structural biologists is a person who uses X-ray crystallography or NMR to actually solve the structure of a protein. There are predictors, which are the competitors in this competition. They predict structure from sequence. They use approaches like homology modeling, threading, ab initio modeling. And there are the organizers. So these are the three main actors in this competition. Organizers first announce a call for structures. So it's like call for papers. Now they announce call for structures. They target the structural biologists in this call for structures. So what they want is they want structures from structural biologists. They want to experimentally solve structures, but they want these structures to be kept secret until the competition is over. Okay? They don't want the structural biologists to deposit these structures to protein data bank. So they continue, and this structure determination process, the experimental process, may actually continue until the end of the competition. I mean, they may simultaneously work on their experiments while the structure predictors are predicting the structures. And After the call for structures, they're evaluated or by organizers, and they publish the sequences of these proteins on the web, and the competitors take these sequences and try to predict the structure, and the organizers collect these predicted structures, and then the structures, the actual solved structures and predicted structures are compared together, how well the predictions match the actual structures. Now, this is going to lead us to our next topic, which is, given two structures, how can you determine whether they are similar or not? So given two shapes, for example, this was the actual structure, this is the predicted structure. Are they close? Okay, so this one is fatter, this one is more slim. So here are my two shapes. Maybe this one is more closer than to this compared to this. If these were the two predictions, I would say this pen is the winner. I mean, because it looks more like to this shape. But how do you find this automatically? How do you say that this shape is more similar to this shape? We are going to, this is the problem of structural alignment. Given two protein structures, our goal is to align them on top of each other to find out whether they are similar or not. Okay, I'm going to skip these. Okay, so protein structure comparison problem is another difficult problem in bioinformatics. There are lots of different solutions to this. Even the notion of optimal structural alignment is not universal. What is the scoring function? There is no universally agreed scoring function for structure comparison, and therefore we have many different algorithms to perform structure comparison. And there are many variations in these algorithms in which how they represent the structure. How do we represent a given protein structure? At the atomic level, do we represent it as a backbone structure by only using the alpha carbon atoms? Do we represent it by its secondary structure, by its molecular surface, ignoring the core part, just the molecular surface? So how do we represent a protein structure as a shape is causes variety in these algorithms. And most of them, I mean, like most popular algorithms that were developed like 10, 15 years ago, they just use the alpha carbon atoms, the central atom in a residue amino acid, to do the comparison. Even that problem proves to be a difficult problem, so that abstraction seems reasonable. So they are going to treat, if we have a protein sequence, we are going to get a single coordinate for each amino acid, and that single coordinate is going to be the coordinate of its alpha carbon atom. So we are going to have a sequence of atoms, sequence of points on the backbone, and our goal will be to compare this. And when we are comparing it, there are also different variations. Are we going to maintain the sequence order during comparison? Or are we really going to compare them as shapes in which sequence order cannot be observed? I mean, for example, I have a structure like this, and a certain part of the structure is similar to another part of in another structure, but in a reverse way. Maybe the sequence order is not made, or maybe part of the sequence order is same, but in the other structure, the part that is similar here is reversed in terms of amino acids. So are we going to maintain the sequence order? This is what we were doing in sequence alignment. When we were aligning sequences, we could not have matches like this. For example, a structure, when we were aligning, we cannot have alignments like this in sequence alignment. Okay, we cannot say this part of the sequence is similar to this part, and this part of this sequence is similar to this part. We cannot say that in sequence alignment. We need to maintain the sequence order in sequence alignment. But maybe in structure comparison, we may allow such things. Maybe Structurally, this is similar to this part as a structure. These are helices and these are sheets. Maybe sequence order preservation may not be an issue in protein structure comparison. And we can use the actual geometry. During the comparison, we can just use the shape, I mean the coordinates only, just treat them as shape, or we can also treat the physiochemical property, we can consider the physiochemical properties of residues during comparison as well. Okay, these shapes are similar, but one of them contains all polar residues. I mean, in terms of shape, it's similar, but it's a surface shape. The other is a core shape. Are you going to consider them still similar shapes? So there are lots of issues, different varieties in protein structure comparison. And here, when during comparison of two protein structure, the key problem is similar to sequence alignment to find the matching correspondence between the amino acids. Which amino acid in this structure matches which amino acid in this structure. So the problem here is to find this matching. Again, we are going to have a one-to-one matching. So finding this correspondence is the difficult thing, and that's the key problem in structural alignment. Here, there's another problem many people consider difficult, but actually it's an easy problem, which is after we have the matching of residues, the other thing is going to be how to superimpose them. Meaning that you are going to have, consider these two shapes, okay? This is like this. In the three-dimensional coordinate space, it's lying vertically like this. And this one is lying horizontally like this, okay? Now, you determine that in terms of shape, they are similar, okay? When we say they are similar, as you can see, we do not care how they lie, where they are in this 3D space. One can be here, the other can be here, here. It doesn't matter. We compare them as shapes. And as shapes, their position, their orientation is irrelevant. So this shape similarity is rotation and translation invariant. It is, you just say this shape is similar to this shape. You do not care about its orientation. So after you find, so the correspondence problem is that you say that, okay, this cap part here matches this cap part. The bottom part here matches the bottom part here. So in the alignment problem, we provide this correspondences. Which part matches which part. Then after you have this correspondences, the next problem is how do we change the position of this second structure, its position and orientation, so that we put these matched residues as close as possible in 3D space. This is the superimposition problem. So how am I going to, it's like saying, bring this 30 units to the right and for example, 20 units up and rotate it 90 degrees, and then you can see that these two shapes are actually similar. So this is called superimposition problem. And this problem was a difficult problem actually. And it's also another, this is called superimposition of point sets. And luckily, this is not an NP-complete problem. A linear, you're expecting this is going to be a difficult problem as well, but it's not. There's a linear solution, not even quadratic, okay? There's a linear solution which can find the best transformation matrix, best position replacement and orientation change parameters. It's going to find you so that the corresponding amino acids are going to be as close to as possible to each other. Here, if the shapes are exactly the same shapes, we can put the corresponding amino acids exactly on top of each other. Okay? If the shapes are exactly the same shapes, what we can do is, after displacement, the amino acids can be exactly on top of each other after this process. However, what happens if they are not exactly similar? What if they are somewhat similar? For example, it's like this. If they are somewhat similar, for example, like this, these two pens, okay? One of them is longer than the other. So it's not possible to put the bottom parts on top of each other and at the same time put the caps on top of each other. You are not allowed to shrink the shapes, bend the shapes. So these, at this protein structure comparison, the shapes are considered as rigid bodies. You are not allowed to scale them, bend them. You're not allowed to distort them. So here, if you say that, I mean, this superimposition problem, you can say, see, it's not a very easy problem itself. I mean, we have a linear time solution, luckily, but the problem is not very easy. For example, if you want to put these two on top of each other, these two are, the top parts are going to be far away from each other. So is this solution, this is not a very good superimposition. How can you, what is the best way? So you need to put the shorter pen a little bit up. So, I mean, maybe this may be a better solution as superimposition than this one. Or how are we going to determine which solution is the best? We are going to talk about measure in that regard, which is called the root mean square distance, RMSD, root mean square deviation. So it's like this. Given 2 point sets, here I have a point set consisting of 4 points. So this is one protein structure. Let me have another protein structure with a different color. Let me make them a little bit similar, but not that similar. Okay, these are my two shapes. Here, the alignment problem is to find the correspondences. And the superimposition problem is after you have the correspondences, to put this on top of this so that the root mean square deviation between the corresponding points are going to be minimum. So how is this root mean square deviation defined? It's like this. If you place this same structure, rigid body transformation, without rescaling it or bending it, for example, if you put this, and I assume the alignment problem is solved at this point, meaning that this one, or let me use lowercase, uppercase letters. So this A, B, C, D, these points are matched to their corresponding capital letters, A, B, C, D. So the alignment problem is to find these point correspondences. Okay, maybe this could have been matched to this capital A as well. So there may be multiple matchings. We may have gaps in this matching. They may not have the same exact number of points. But to show you the superimposition part, to show what RMSD is, I assume the alignment problem is solved. We have found the correspondences using an alignment algorithm, structural alignment algorithm, and the lowercase vertices are aligned with uppercase vertices. Now the question is, we need to find out, okay, you have your alignment found out that these structures match with each other like this. And now what we want to ask is, are these two shapes really similar? Okay, you have matched them. You have matched them point by point. You have provided correspondences. But how similar are these shapes? In order to find how similar they are, we need to take this, put it on top of this shape, and we compute pairwise distances between matched points. And root mean square deviation is actually, its definition is in its name. Okay, so square deviation. So we are going to get, or square distance, we are going to get the square distances between each pair of points. We are going to take the average of these square distances, mean square deviation, and we are going to take the square root of that distances. Okay, so this provides a measure of how close these shapes are going to be. And for example, right now at this point, if you want to compute the root mean square deviation between these two shapes, when this red structure is here, it's going to be like this. We are going to compute the distance between A and A squared plus distance between B and B squared plus distance between C and C plus distance between D and D squared divided by 4 and take the square root. Okay, so this is our root mean square deviation. Now, when this red structure is here, this root mean square deviation is going to be high, right? I mean, the distance between A and A is this. Distance between B and B is this. C and C, and D and D. Now, the superimposition problem is this. You are, by allowing translation and rotation on this structure, or on this structure, any of them, it doesn't matter. By repositioning it and rotating it, how small can you get this RMST? What is the minimum RMST that you can get by rotating and repositioning this second metric? Can it be 0? If the shapes are same, it can be 0. Okay? But what if the shapes are not exactly the same? It's not going to be 0. And we will be interested in the minimum RMST. So which is, and luckily, this minimum RMST can be found in linear time. I'm not going to talk about the details. It's a mathematical technique which there are different ways. There are a couple of different approaches, but one of them uses the singular value decomposition of the covariance matrix of these coordinates. So it's a complicated technique, but all you should know is that it's fast. It's very efficient, and in linear time, it can give you the translation and rotation to put this like this. So this is A, for example, maybe B, C, and D. So it's something, maybe it's going to be something like this. But I mean, immediately, if I do it, you can see that it's not the minimum RMST. Why don't you put it a little bit higher? I mean, if this is not the good superimposition, this is not the best, because by taking this structure maybe a little bit higher, well, if you put it higher, these distances are going to get larger. Maybe it can be the minimum RMST. So, but you cannot be sure. We need to run that algorithm to superimpose these two. But what it's minimizing this measure. Okay, it's not minimize. Some of them, for example, if you may put this A on top of this A exactly. You can put a point on top of another point exactly, but doing so, you may make this point far away from D. I mean, if you want to put this A on top of this A, this D is going to get far away from this D, so you are going to, while trying to decrease this, you may be increasing this part. So this algorithm takes care of this. It considers all these cases. It gives you the minimum. I mean, it gives you the one which is going to have this measure, this RMST minimum. And the RMST is going to be the square distances of these distances, okay? Yes?
This is kind of search problem, yes? Since we don't know exactly if these two ways are the points that match together or not, maybe...
That's the alignment is the alignment does not know, I mean, the alignment problem solves the matching problem.
So it doesn't know which points.
I mean, minimizing RMST, this fast solution assumes that a matching is known. It doesn't search. I mean, it knows it's going to compute distance between A and A. I mean, the distances we are going to compute between which points are known. And this algorithm works with point sets that have exact same number of points. Okay, this one has 4 points, the other also has to have four points. But in alignment problem, we may have a protein of length 100 and 150. Now, in the alignment problem is much more difficult. Which of these amino acids are going to be matched? I mean, which one of these amino acids in this 100 residue protein is going to be matched? With which other amino acids in this longer protein? That's the alignment is the difficult problem. After you know the matching, after you say that these amino acids are going to be matched with each other, you can use them all. And the RMST, the superimposition problem, takes into account only the matched residues. You ignore the unmatched parts because there's unsimilar structure. You only consider the matched residues during superimposition. And the matched residues are going to be put as close to each other with the superimposition technique. And the superimposition can be done very fast, linear. If you have 4 points, it just takes operations on the order of 4. I mean, linear on the number of points in one of these sets. So RMST, finding the minimum RMST after the matching is not a difficult problem. However, here this slide says the complication is that, the difficult thing is that we do not know a priori which amino acid in molecule B corresponds to a given amino acid in protein, in the other protein. So that's the difficult thing. So let's have a break, a 10-minute break, and we are going to continue with some algorithms that is going to provide us the matching as well.